Alrighty, let's take a look at some of these homework questions. Alright, first one is the integral of 2x squared plus 5x minus 9. Alright.
Oh, broken.
What?
It's a sensitive creature.
Hey, Danielle.
Did you get weird?
They all have their. Oh yeah, I know. I guarantee you.
It's supposed to go in the dark.
Oh, you're gonna get yours in the dark.
So, I better not touch this wire. Is that what it's telling me, I think?
Yes.
It's broken, the whole setup.
Okay, whatever. All right, here we go. All right, on an integral like this, here's the rule. If the numerator has degree greater than or equal to the degree of the denominator, the first step is to divide. Okay, you want to do a long division. And if you'll notice on the practice test,
Number 6.
yes, on the practice test, I have a section on there that says, what's the first step in doing that integral? Find the first step in evaluating the integral. And number 6 is x squared plus 3x plus 6 over x plus 5. It's the same thing. The first step is to divide. And on the multiple choice test, you'll have A is let u equal x squared plus 2x. B would be divide, and C would be let u equal something else, and the answer is divide.
Oh, you don't
That's
have to
pretty
go.
much your first.
No, you just have to tell me the first step. So what are we going to do here? Divide.
Yeah.
So 2x squared plus 5x minus 9 divided by x minus 3. Okay? You don't even have to do the division, you have to just say divide. All right? But let's do it.
Easiest math question.
What's that?
It's gotta be the easiest math question.
No, there's.
There you go. All right. It's only because I like you guys. And one other thing. On the syllabus, if you check out the syllabus on WebAssign, there is a syllabus there. And your grade, 10% of your grade is the homework. Okay? So keep that in mind.
I wish that was the case last semester.
You know, well,
But that's it's optional.
what's that?
That is optional.
You see, I don't know. And the syllabus, I said 10%. And I said optional?
I thought you said
Yeah.
you said it wouldn't hurt us.
10% is
I know.
optional.
Oh, okay. Now it's coming back.
Well,
You said that
if
if
you get a
the
90,
end, if
it's
you're
an A
close
in
enough.
class.
It'll help you, but it won't hurt you.
Okay. We'll do that. It'll be 10% if it helps.
But isn't a 90 an A anyway?
90's an
So that's why 10% is optional, because if you get an A.
A. Well, no, well, the thing is, if you have that 88 average, or 87, let's go with an 87 average, and you have really good homework, that'll give you the A. So that's pretty good.
Yeah.
I'm gonna do that.
Danielle?
On the resources, you only have 5.2 and 5.3 in
That could be,
there. The Dropbox thing.
yes.
Yeah, last time.
Yeah.
The class
Last time was a total disaster. Nick has a couple things on YouTube.
I have a
I'm hoping Nick gets here and he can direct you to YouTube.
I went to the YouTube channel and there's something.
This thing wasn't working.
Well,
Oh, so now.
Yeah.
yeah, last class, we couldn't do
He
it.
recorded the class that I was here.
What's that?
He recorded the class that I was
Oh.
here, so I already know what happened in my class.
The last class was a mess.
Yeah, that was a disaster. We couldn't get anything going. And then this setup from the IT department over there, because I yelled at him today. I said, I sent an email last week on Friday. Nothing happened, so please get somebody over here to fix this, and this is their fix. So, I don't know.
kind of a work.
Yeah.
Sounds like a cop out.
Yeah. All right, anyhow. So this would be a question on the test. The answer would be to do the division, okay? It's a long division.
You
Yes.
can put a chair so
The stool?
What's that?
the stool so you don't have to step on the.
You think that'd be better?
Yes.
You think I'm uncomfortable like that?
No, to push the cord to the wall so you don't touch the cord.
I don't think, he doesn't look more comfortable.
Yeah, this is all right. We can do it.
You don't have to sit down, you can just push it out.
You turned to the wire, what are you?
Fix it on the screen,
Sorry.
It's okay. No, that's all right, leave it there. Now we'll get it back, hopefully.
Try to fix it.
TV, I think the TV is a problem.
No, the TV is on.
Oh, you got it.
It just had it.
Wiggle it a little more. It turned on.
When I graduated from high school, I was like 2 years older than him, but I went back and helped him coach for a while.
Clearly it's the wire.
Around the entire time, just shooting pucks.
Ball out.
You think it's that part? Maybe it's that part.
I know
Ball up.
Ball dock.
It's a ball up.
No, it's
Dude, I played the dock for like.
I've been doing this. Yeah.
Not much of a ball player.
We had it there, real brief, you had it for a second. So there's one,
Plus C, goes to point 0, 0, so you know it's plus C. You have to kind of plug this in the equation.
I like this.
there.
Don't.
All right, here's the deal.
Plug in.
Nobody can breathe the rest of the class, okay?
I think they'll go over.
Yeah, we're gonna go over the whole thing.
All right, do the long division. X goes into 2x squared, 2x times. Okay, multiply. And then subtract. 5x minus this negative 6x is 11x. Bring down the next. Okay. Multiply by 11. Subtract. Okay, negative 9 minus this. Be 24. This integral becomes this integral. 2x plus 11 plus 24 over x minus 3. Okay? Quotient plus remainder over divisor. Okay? And once you put it in that form, then the integral is simple. Integrate 2x, it's 2x squared over 2. Integrate 11, it's 11x. This integral is 1 over u du form. U is x minus 3, the du is dx, so you get 24, natural log, absolute value, x minus 3. Okay, plus c. And that's your answer. That's how you would do a problem like that. Okay, any questions on that? Okay? Okay, number 12. This is the integral of cosine t over 3 plus sine t. And the key to doing the integrals in general is to identify a u and a du to go with it. What you're always trying to do is take the integration that's given and change it into one of the integration forms that we have. Okay? And what you have to be able to do is look at this and see that if you let u equal 3 plus sine, the du, the derivative of this, is cosine t dt. And that's exactly what we have up in the numerator. Okay? This problem is much more difficult to do if you don't have the cosine, because then I couldn't do this kind of thing. And we'd have to resort to something else like conjugates to multiply numerator and denominator, which is exactly how you would have to do that integral if you didn't have the cosine. So you rewrite, you identify this, make the substitution. 1 over u, this is u, du. This is an integration form we have. It's 1 over u du form. Therefore, you get natural log, absolute value, u, which is 3 plus sine, plus c. And that would be the answer. Okay. Wow, it looks nice when it works. Okay. Everybody else set on that? Yes,
I
Danielle.
don't really get the U and D. I get the U, I don't get the DU.
Well, if you let u equal 3 plus sine, you have to take the derivative of that. And actually, I am skipping a step here. There's u. du dt, the derivative of this, is cosine.
Is that cosine 3x too?
Pardon?
What happens to the 3?
Derivative of a constant is
Oh,
0.
yeah, yeah.
Okay? Therefore, du, you bring the dt on the other side is what you do. Bring this over on the other side. The nice thing about the notation, this is Leibniz's notation, the nice thing about his notation is the du dx, the dy dx act as fractions. They're not really fractions, they're limits, okay? But the notation is set up so they act like fractions and suggest these properties that you can use. And that was the really good thing about Leibniz's notation, as opposed to Newton's notation, where he had dots in these. Notation was very, very difficult, right? And very difficult to teach and learn. Mathematics in England went down the tubes after Newton. There was nobody after Newton. The best mathematician was Hardy after Newton, and the only reason his claim to fame was he found this guy in India who was an incredible mathematician. He didn't do anything much himself. So,
How does cosine or cosine become 1 over u?
when
Once you
I
plug in the du.
du is cosine t dt.
Yeah.
Okay. Here's cosine t dt.
Yeah.
I'm going to replace it with du.
Yeah.
du over u.
Oh, so then you just
Okay.
have 1 up there?
Why is it doing this?
Yeah, du over u.
I got too close to it. Is that it? Yeah.
It doesn't like that.
What you should realize is what I have here is exactly what I have over here if you look at the substitutions. What's u equal to? 3 plus sine. There it is over there. What's the du equal to? Du is equal to cosine t dt. This and that are the same. They have different form, but they're identical to, they're equivalent to each other.
Yeah.
You still don't sound convinced, Trent.
Well, yeah, I am. I'm just, because the cosine dt is substituted for the du, then you just have a 1 up there because you need.
Oh, yeah, okay. Actually, I could have written it du over u.
Right.
Okay, matter of fact, a lot of books prefer that. I prefer to do it in 2 steps, 1 over u du, as opposed to du over u. That's all that is. It's the same thing.
Yeah.
I think you just set up the infrared sensor when you did that.
Was that what happened?
And close to it.
It's the brightness.
Yeah.
Basically, it's brightness. If you get closer, it's darker, lights up.
Serious?
Yeah, if you block it, it's gonna light up more.
Wow. Pretty cool. All right. Hey, let's do another one. Pretty nice. This is in 5.8. It says find the integral, do the integral. Integral of 1 over x square root of 9x squared minus 1 dx.
Oh, we just did that one.
Yeah, we did it before class, but we didn't do it here. So let me do it here for everybody. This one's a little trickier. You're going to have to look at this and see that it looks very similar to the inverse secant form that we had last week. It's not quite there because of that 9x squared, all right? And what you have to realize is if you let Nick's here, all right, I got the thing in there, and I am recording. So this is how they rigged it up, Nick, as a temporary fix, because apparently the whole outlet thing is not good.
Awesome.
Yeah. All right, you're going to have to see that this is pretty close to being that inverse secant. As a matter of fact, we can get to the inverse secant form from here. Recall what the inverse secant is. It's the integral of 1 over, either have the absolute value here or in the answer, okay, u square root of u squared minus 1 du. And that's equal to inverse secant. And like I said, the absolute value has to be somewhere, either here or in here. Okay, let's see. So we want to go from this, what we're given, into this form. That's the integration form we have. How do we get there? Well, if we're going to get from here to there, the u has to be 3x. Okay. The du has to be 3 dx. I don't have a 3 dx, but I can get there easily enough by multiplying by 3 and by 1/3.
Why do we need the 3 again?
Say that again.
Why do we need the 3?
Because it's 9x squared inside that square root. In order to go from here to here, I'm going to have to let u equal 3x. It's 3x quantity squared is what it is. So the u is the 3x. Now, but I'm not done yet, because you notice this is u as well. And we said u is 3x, but I only have an x here. So I'm going to have to multiply this by 3 and by 3 on the outside so that I have the 3x that I need for the u. Okay? And now, when I do this out, these 3's will cancel. I'll be left with the integral of 1 over u square root of u squared minus 1 du, where the du is this 3dx. Okay. I have my inverse secant form. That's what I want. That's equal to inverse secant u. And now we noticed when we did this before class that Webassine wanted the absolute value here in the argument, so that's what we're going to do. The argument here will be the absolute value of 3x. Okay, but you can take the 3 out front. So the exact thing that Webassine wanted was this. This is the u here. Okay, but they wanted the absolute value because you have to have an absolute value here or here. Why? Because of the way inverse secant is defined. You'd have to go back to Calc 1 when you define the inverse secant and look at where the quadrants are in order to get that. But that's a Calc 1 thing. Go ahead. Somebody.
What's the like 1 over a form?
Well, that's when the a is over here and you get the u squared minus a squared. And that would be the 1 over a. See, if you had this,
Oh, so if that's not a 1, if it's like 25, then
yeah, exactly.
a would be 5.
Yeah, exactly right.
Okay.
This a here is now
But
3.
because it's a 1, you don't
Yeah.
need that form.
Correct.
Because it'd be 1 over 1.
Yes, correct. Good. Okay, what do you think? You all set with that one?
Yeah, I was just confused because it didn't give you, all the other ones it gave you the formula, like these two.
Oh, you don't have the inverse secant.
Yeah, so I don't have.
Where'd you get those?
Oh, I just copy pasted from the, when it says to watch it, like it's in the notes.
Oh,
I just put it on the side, so.
okay, well, there's 2 of them, but there is one more. And we did do the third one, and that's the inverse secant.
Okay.
Yeah. Okay, and we got another one here, which is number 9, integral of e to the 2x over 9 plus e to the 4x dx. Now, see, here's the thing. When we look at the test, I'm not going to give you, this is a tricky kind of a thing here, all right? You're going to have to look at this and say, geez, what the heck kind of form do I have here? And if you can look at this and see that, well, if you let u equal e to the 2x, this is a u squared. Okay? This is u squared. The e to the 2x dx, du is going to be e to the 2x times 2 dx. If I multiply by 2 and by 1/2, what I'm going to get is 1/2 the integral of 1 over 9 plus u squared du. And that just comes from practice. You just have to do enough of these to see that if I let u equal e squared, here's my du. What kind of a form is this? What form is this?
Tangent.
Inverse tangent. Very nice. That's what the form is. This is an inverse tangent form. Okay? And now we do have an a. We have an a squared here. What's a equal to in this case? 3. Okay, so we have the 1/2. And we have the form for this, which is 1 over a, inverse tangent, u over a, plus c. That's the form we have. I think that's the form you have in that paper there for that one. So that's 1/6 inverse tangent, u, where u is equal to e to the 2x, divided by 3, plus c. Now, I'm not going to give you a problem like that in the test, okay? I just won't. Okay? It's too much of a trick. I don't think it's all that useful, although it's kind of nice on the homework to get you to think a little bit outside the box and to look at different things like that. No. All right. Any other questions on homework? Anybody else? Anything else at all? Okay, let's finish up the chapter. We have a couple things to finish up in the chapter, and let's do that right now. First thing we have to do is the hyperbolic trig functions. And we're going to do two of them. The first one is sinh. This is called the hyperbolic sine. Okay, it's pronounced sinh. It's equal to e to the x minus e to the opposite of x all over 2. Okay, that's what it's defined to be. It's got a graph here. Let's take a look at the graph of this thing. If you look at e to the x, this is e to the x graph. E to the opposite of x. How is this graph, e to the opposite of x, related to this graph, e to the x? How are those two graphs going to be related? They're not really inverses.
Are they upside down?
Not upside down. It's a reflection about y-axis. It's the y-axis. When you replace x with its opposite in any function, the graph that you're going to get is a reflection of the original graph about the y-axis. That's always true. Okay? Now, if you have a function and you replace x with its opposite, and you get the same graph, what does that tell you about that function? Oh, John, you're good. You know that? Even. That's exactly right, because if you replace x with its opposite and you get the same graph, that didn't change anything. That's what an even function does. Replacing x with its opposite causes no change. The graph must be symmetric with respect to the y-axis, because replacing x with its opposite causes that reflection. And if there's no change, it must have been symmetric with respect to the y-axis. Typical graph, typical function would be y equals x squared. Even function, replace x with its opposite, no change. Opposite of x squared, still x squared. And what do you get for a graph? That parabola, symmetric with respect to the y-axis, okay? So when I replace x with its opposite here, I'm going to get a graph that's going to be a reflection about the y-axis. Now, it's not going to be the same graph because e to the x is not an even function. It's going to be this graph. Okay? Wow, I nailed it right on the button there. Okay. This is 0, 1. Okay, what we're going to do to generate the sinh function, we're going to take the difference in the two, okay, and divide by 2. So here's what we got. They're the same here. So when I take their difference, they're going to get 0. Okay? Now, as I move away from the origin to the right, what it's going to be is this graph minus this graph divided by 2. Well, what it's going to do is look more and more like half of this graph, because this guy's going to have a decreasing importance. Okay, as we move away from the origin, e to the opposite of x is going to go to 0, and the graph is going to look very much like this, e to the x divided by 2. So it's going to look something like this over here. As I go to the left, it's going to be this graph. Okay? When I take this one minus this one, this is e to the x now down here, minus this, I'll get a negative number, okay, and divide by 2. It's going to look like this. Okay? This is the sinh function. Okay? Let's take its derivative. If y is equal to this, the derivative of sinh, well, what do you have? You have this minus this over 2. That's a constant. Take the constant out front. What's the derivative of e to the x? And what's the derivative of e to the opposite of x? Times negative 1, because you have to take the du, so that changes that to a plus. You get this. And what that is the cos function. That's the hyperbolic cosine function. Let's take a look at its graph. instead of subtracting these two, we're going to add these two and then divide by 2, okay? When we add them and divide by 2, we're going to get a point here. Okay, add them, you get up here and divide by 2. And basically it's going to look like this. It looks like a parabola. It's not. It doesn't have the same properties of a parabola. But it's a very important function, okay? This graph of the cosh function is called a catenary. If you take two telephone poles, okay, and string a wire from this one to this one, okay, that wire will be in the form of it looks like a parabola, but it's not, a catenary. It'll have the properties of a catenary, okay? So if you want to minimize that length or do something with the material that the wire is made from so you can minimize the length necessary to go from here to here, that would save an electric company a great deal of money and you'd probably make a fortune. But anyhow, that's a catenary, okay? Actually, there's quite a few objects that have this catenary curve that are used. But anyhow, we're not going to get into those. What we are going to do is take the derivative of cosh. Derivative of cosh, let's see, derivative of e to the x. Derivative of e to the opposite of x. Yeah, is e to the opposite of x times a negative 1, so that becomes this. Whoa, what is this equal to? Sinh. Here we go. The derivative of sinh is cosh. The derivative of cosh is sinh. Okay? All right? That's the way it works. All right? They're called hyperbolic trig functions because the properties they have are very similar to the properties of trig functions. And I say similar because they're not the same. Half of them are off by a negative. Okay, so they're similar, but they're off by a negative. Like with the trig functions, the derivative of sine is cosine, but the derivative of cosine is the opposite of sine. Not true here. Derivative of sinh is cos. Derivative of cosh is sinh. You know what I mean? So they're off a little bit by that negative. Okay. One other thing we want to be able to do with these is to integrate these. Okay. Let's go to the integral of sinh u. What do you think the integral of sinh is? We're looking for a function whose derivative is sinh. That's what that integration symbol is, as an antiderivative. We're looking for a function whose derivative is sinh. What function has a derivative of sinh? Cosh. This is cosh u plus c. That adds one more integration form to our list. And believe it, what's that? Yeah. Yeah, because the integral of sine is a negative cosine, so it's the opposite. And believe it or not, the next one that I give you is the last integration form that we're going to need. It's the last integration form you're going to need for a long time, okay? Because what we're going to do the rest of this course is to develop technique to take an integral that's given that's not in one of these integration forms and transform it into an integral that is one of these forms. In fact, we're going to do that in a minute too. Another topic we have to touch on. Calc 3, you do integrals. You need double integrals and triple integrals. You do applications of the integral to 3 space and do problems with them, but no more integration forms. Okay? And diffie-cubes, you need to integrate all over the place, okay? Lots of integrals to do, but you know what? They're all things that we've done here. So you won't need any more. And the last one is the integral of cosh is equal to sinh. That's correct. Pretty simple. So you'll notice in that piece of paper that I gave you, aha, number 14. What form is that integral in number 14? Cosh u du is exactly what it is. What's u? 4x. What's du? 4 dx. So what would you have to do that integral? You'd have to multiply by 4 and divide by 4, take the 1/4 outside. What is the answer to 14? Oh, I left the multiple choice in here. Well, it's probably the actual test question.
You can keep it on there. It's okay.
What's that?
You can keep it on there.
No. Yeah, I'm gonna have to go back and change it to a hyperbolic cosecant or something. No. 14, the answer is going to be A is correct. Okay? Because that 1/4 that you have to multiply comes outside. The 4 that you multiply inside becomes your du.
You have another one.
Oh, of course. I'm sorry.
That's not it.
You're welcome. All right, how are we doing so far?
Good.
That well, huh? All right. Now, one more thing we have to do here, and that's to do an integral like this. Here, let's take a look at some of these. Let's suppose you have this integral to do. Let's do a couple of these here. All right, somebody tell me how to do this integral. What do you do here?
You take out this 4.
What's that?
Half.
U to the 1/2. U is equal to what?
X minus 1.
Perfect. U is x minus 1. The du is dx. There's no need to even multiply by anything. You have it. So you do just what they said. This is u to the 1/2 du. It's a u to the n form. Okay? The integral of which is u to the 3/2 divided by 3/2 times 2/3 plus c, and replace u with x minus 1. And that's the answer. Okay? Not a problem.
Could you just put it down a little bit? It's on the recorded thing. Yeah, it's good.
Okay, let's do this integral. What do you do here?
To the 1/2.
What's to the 1/2?
Oh, that square root thing.
Okay, the x squared minus 1 to the 1. Okay, I can rewrite it that way.
Then we solve for
And I was gonna say
And then what are you going to say? No, you can't do that. That's kind of illegal.
Just do u.
What's that?
Like make one of them u.
Yeah. What's u?
X squared minus 1.
Perfect. Perfect. Absolutely perfect. U is x squared minus 1. The du is 2x dx. Not a problem. We have an x here that can serve as part of that du. We got to multiply by 2 and by 1/2. We get 1/2, the integral of u to the 1/2 du again. It's another u to the n form. Okay? Yes?
Do you know if you need a du?
You always need a du to go with the u. That's always the case. You're always looking to take the integral that's given and change it into one of those forms. And now we've got about, I don't know how many forms we've got, 15 forms or so, something like that in there. That's what you're aiming for all the time. And here's one of those forms. And now I can integrate it to get u to the 3/2 again, times 2/3 plus c, 1/3 u, x squared minus 1, 3/2 plus c. And by the way, how do you know this is correct? How do you know this is right?
Do the derivative.
Do the derivative. Thank you. That's exactly what you do. Okay, if you take the derivative of this, you will get the original back again. Let's do it. You got 1/3 constant. Take it out front. To take the derivative of this u to the n form, the derivative is 3/2 u, subtract 1, take the derivative of x squared minus 1. After all, how you take the derivative of u to the n? It's n u n minus 1 du dx times the derivative of x squared minus 1. The derivative of a constant is 0. Forget about it. 3's cancel. You're left with, 2's cancel, 2 by the way, x square root of x squared minus 1. That's exactly what you started with. Okay? That proves that that's the answer. Yes?
So why did you do the half and the 2x thing? Like, you know what I'm talking about?
This one half? This one half?
Right next to it.
This guy here?
No, right next to it. Like, middle, in the middle. No, and
Where's
yeah, right
Okay, because by letting u equal x squared minus 1, the du is 2x dx. I only had an x dx. I need 2x dx so I can get the du in there. And how do I get a 2x from the x? I multiply it by 2. But I can't just multiply it by 2 without compensating, multiplying by its reciprocal 1/2 on the outside.
You're essentially multiplying by 1.
I just
Yeah.
don't know why you have to have to do it.
You have to have the 2x to get the du so you could put it in this form. If you don't do that, you don't get this form. And you need this form to do the integral. Every integral that you do, you're going to have to eventually end up with one of those integration forms. You have to keep that in mind. Yes?
So what's the first step, like, on number 8, what would the answer be?
That's where I'm headed. You ready? We don't know how to do 8 yet. This is where I'm headed. So you got this one, you've got this one. Now let's take a look at this one. Suppose you have this. 8 is a plus. I might as well do number 8. Let me do number 8. Suppose you have this one. Well, it's not the first one because you got that extra x in there. And it's not the second one because the inside the radicand here is not x squared plus 1. If this had been x squared plus 1, it'd be fine. It'd be u to the n, do just what we did up here, same thing. But we don't have either of those. This one is a special case, okay? This is one where you're going to have to make a substitution and change that integral. Now, in my opinion, this is a topic that belongs in 2 chapters from now when we do techniques of integration. But for some reason, the authors put it in this chapter here. I think the reason is because in the next chapter, when we do applications of the integral, there's a few integrals where you're going to use this, okay? So they put it in here. What we're going to have to do is make a substitution, change the integral around, and hope that we can end up with one of those integration forms, okay? I'm going to let u equal that square root. All right? I'm going to square both sides. I'm going to find dx. Take the derivative of each side. Okay? And now I'm going to make the substitutions. The bottom line is what I want to do here is get rid of the square root. If I can get rid of the square root so I can use a distributive property, that'll probably help me be able to set this thing up in an integral that we can do. Okay? So let's see what happens if I substitute now in for this. X, that's u squared minus 1. That's what x is. Solve for x. Square root of x plus 1, that's u. Dx, that's 2u du. What I've done by doing this is eliminated the square root. Okay? What I've done is enabled me to do the following. Watch this. I can take the 2 out front. I've got a u squared times u squared minus 1. Now I can use a distributive property. I don't have a square root anymore to give me u to the 4th minus u squared. Okay? So what I'm doing here, this is something we're going to do in a couple of chapters too. This kind of thing where we take the integral that's given. It's not any of our integration forms, but we're going to transform it. Okay? By making an appropriate substitution. Did you guys do this during the day? Did you do one of these?
I just have a question.
Oh, go ahead.
U times the square root of u is u to the 3/2.
U times the square root of u is u to the 3/2. Yes, it is.
I did it differently then.
Well, this is not u and the square root of u.
I made it that way. I did something weird. I never mind.
Did you end up with the right answer?
I didn't finish it.
There are a couple other ways of doing this.
Yeah.
Okay? You could let u equal the x plus 1.
Then I solve for x.
And then you solve for x and dx and do that. I prefer letting u equal the square root and eliminating the square root that way. But there are other ways to do it. Okay.
What you did was you squared the u. Is that after? That has nothing to do with the actual integral?
Would say that again.
U squared equals x plus 1. That's separate from that integral. You're just changing it, right?
I'm changing it, yeah. Yeah, I haven't done the integral yet at all.
How about 2u du equals dx? How'd you get that?
I took the derivative of both sides. Bless you.
Oh, you just took the derivative.
I just took the derivative. Okay. Now, let's do the integral. U to the 5th over 5. U cubed over 3. But what's u equal to? Square root of x plus 1. I get this answer. U is x plus 1 to the 1/2. So I get x plus 1 to the 5/2 divided by 5 minus u to x plus 1 to the 3/2 over 3 plus c. I know it's a pain in the neck, but believe it or not, if you were to take the derivative of this, you'd end up with this.
Wow.
I know, it's stunning. All right, I want to point that out. It's what you have to do sometimes is do something like that to change the integral. It just can't be done in the way it's given. You have to change it. This is one of those kinds of things to change, this kind of substitution.
Would you give u squared minus 1?
U squared minus 1 came about by solving for x from here, subtracting the 1 from both sides. And then replacing this x with the u squared minus 1.
Okay.
Alrighty?
That's ugly.
It is. But here's the deal. Do I ask you to actually do one of these out? No. In number 8, I want the first step. So what's the answer to what's the first step in solving that integral in number 8? Letting u equal the square root of x plus 1, and that would be one of the answers, okay?
What would you say?
You wouldn't have x plus 1 as another answer, right?
Well,
No, because it could be done that way.
so u would equal whatever is the square root of?
Yeah.
U squared, so what was it, u squared plus 1, is that what it is?
U is equal to the square root of x plus 1. That's your first step.
Right.
Although there are other possibilities too. But that's what I would put. Now you got to be careful, because if the integral is x times the square root of x squared plus 1, that's not your first step. What would your first step be? And well, we did it. We did this here. The first step in doing this one, if this is the problem, is to let u equal this. Okay? Because you have the du to go with it. You don't have to do this substitution for the square root to get rid of the square root, because you can deal with it this way by letting u equal x squared minus 1. Okay? That's what I did here. So be careful. All right? Be careful on that. All right? Because you may have that one on there and this one on here, and you just kind of have to make sure you keep them straight. Okay, how are we doing? All right, now we're going to do the 6.2. We're going to jump over to 6.2, chapter 6.2. So here we go.
And this is part of our test.
Yes, you'll notice at the very end of the practice, the last two, we got mosquitoes. You add an E at the end of mosquito for mosquitoes? Is that look right? That doesn't look right to me now.
Mosquitoes,
Mosquitoes. I don't know.
mosquitoes.
Well, it's not that. It's the E at the end that I'm questioning. I don't know. All right, who cares? All right, fine. All right, here we go. These are two applications that we're going to do in Chapter 6. This is what we do in Chapter 6. There's two applications that we're going to do. The applications are population growth and the radioactive decay. I'm going to do both of those right now. Okay? You'll get one of those on the test for sure. All right? Population growth. A simple model for population growth is the following. That the rate of growth of a population, dp/dt represents how fast the population is increasing. It's derivative. It's what a derivative tells you, how fast something is increasing or decreasing, is proportional to the population at any given time. Okay? This is a differential equation. It's a very simple model for population growth. Okay? And let's further suppose at t equals 0, the population of whatever this is initial population, some constant piece of naught. So at t equals 0, our population is the initial population. Okay? What we want to do is solve this differential equation. We'll graph it. It's a pretty good model over a short period of time. As a matter of fact, if you put some bacteria in a petri dish like so, you give the bacteria some food, they'll grow according to this model over some period of time. Okay, it's going to be an exponential growth model, something like this. But what happens is this model keeps it going infinitely. Okay, there's no biological organism that's going to maintain that kind of exponential growth over an extended period of time. That's what's wrong with this model. It's good for a short period of time, but it's very poor over an extended period of time. Because what happens is food is exhausted, the environment can't support them. There's something called a carrying capacity of the environment, and things happen. They get predators, all kinds of things. Run out of oxygen, depends on what you're doing. But we're going to solve this differential equation for P. We want to find the population at any time T. And then what we also want to find is doubling time. You'll notice on the test, sample test, the very last question is, what's the doubling time? How fast does it take that population to double? All right, but the first thing to do is solve for P at any given time. So let's do that. We've got a differential equation. The first step is to separate the variables. This is what we did at the beginning of this chapter. Take the P, divide by P, take the dt on the other side. Okay. Now, let's integrate it. Okay. That's how we solved the differential equations at the beginning. What's the integral of dp over p? Yeah, what's the integral of 1 over p dp or dp over p? I could have written as 1 over p dp. Natural log, yeah, very nice. Natural log. Now, I don't need absolute value here because when we're talking population, we don't have negative numbers, okay? And we don't have a 0 either, okay? So I don't need an absolute value here. What's the integral of k dt? K is a constant. Bring it out front. What's the integral of dt? T, thank you. Plus a constant. Okay. All righty. Now, let's solve for the constant. We have a point at t equals 0. P is equal to p sub naught. So, substitute in p sub naught. T is 0. We get c. Our constant is the natural log of p sub naught initial population. So here's what we have. Natural log of p is equal to kt plus the natural log of p sub naught. Okay, so we have right now. Yes?
What happened in the second step to the KT? Why is there only a C there?
Why is what?
There's only a C there in the second step.
Because T is 0.
T is 0.
Oh. Keep going.
Did they answer the question? Okay, good. Okay, good. Okay, good class. All right, what we're going to do is solve for p. Now, the way to solve for p here is get these natural logs together. So I'm going to subtract the natural log of p sub naught from each side. Okay. And when I take the difference of two natural logs, that is what? The natural log of? Yes, the quotient. Boy, Trent, you're right. You're, jeez. You're on the money, man. Okay. Now, I want to solve for p. Here it is involved in the natural log. What should I do to both sides to get p out of that natural log situation so I can actually solve for p? What is it? No.
Multiply by the initial p? No.
Ooh, no, you get closer, though. Get closer.
Multiply both sides.
No, that's not going to do it. What's the inverse operation to taking a natural log?
The log. Exponential.
The exponentiation. That's what I'm going to do. I'm going to raise each side to this exponent. Watch this. This is kind of cool. I'm going to go over here to do this. E to the natural log of p over p sub naught is equal to e to the kt. Exponentiation. Okay? They're inverse to each other. E to the x, natural log x are inverses to each other. Okay? So I'm going to raise e to that exponent. What is e to the natural log of p over p sub naught?
Just P over P sub naught.
That's very good. That's exactly what it is. Okay? That's equal to e to the kt. Bring the p sub naught on the other side. P is equal to p sub naught e to the kt. Okay? This is population growth model, the simplest possible model, the simple model. Okay? You'll notice the graph of this, if you take a look at the graph of this, Here's initial population at t equals 0. It's exponential growth. Okay? But like I said, no organism will maintain that exponential growth over an extended period of time. Yes?
Where it says P equals to P sub naught, yep, is that E raised?
Yes. E to the kt power.
So it's P sub naught raised to the E?
No.
Oh.
No, this is a product here.
Okay.
It's E that's raised to this, but this is a product.
Okay.
I brought this piece of knot over to the other side.
Okay.
Okay? Yeah, go ahead.
What if t wasn't 0? Would it be different?
If you, instead of t equals 0, you're given another point, you could solve for that constant and it would be different. In these problems, however, they're always, it's always the same thing. At t equals 0, it's the initial
But
population.
it says t equals 7 days. So 7.
Where's it say?
T equals 7.
Yeah, okay, we can solve that, but we need this first, okay? And then we're going to solve it for p equals 7.
So is that
Or-
the proof almost? Is
That's the proof right there. That would be a proof of population growth. We
so
just did a proof.
We need to know that formula.
You need to know this formula.
Okay.
You need to know this formula right here, okay? This is population growth. Let me just point out that, yeah, if you don't know the formula, then what do you have to do? You have to derive it. So you may as well just know it. It's pretty simple.
again?
What's that?
Okay.
K is the rate of growth. Okay, that's the rate at which this population is increasing. So if you've got a population of bacteria in a petri dish or something that's increasing at 20% per hour, compounded continuously, that K is the 20%.
Which is
Okay.
0.2.
0.2. That's exactly what you would do. Okay? As a matter of fact, this model here will give you this. Watch this. If you put your money in a bank, right? They're not going to give you peanuts nowadays, but anyhow, what they will do, it used to be they would compound it quarterly, 4 times a year. And that simple interest would amount to some other interest a little bit better because they're compounding 4 times a year. They take the interest from that, add it onto your principal, so the next interest-bearing period, you get a little bit more money, okay? And then they would compound monthly, okay? Well, that was a little bit better, okay? A little bit better. You got something called APR, annual percentage rate, and you got something that's actual yield. So something that's invested at 4%, compounded daily, say, amounts to 4.2% maybe, because they break it up into little pay periods, take your interest, add it to the principal, and then that makes it a little bit better. You get exponential growth with that model, okay? But instead of compounding daily, you can compound hourly. You can compound minutely. You can compound every second. And then you can compound continuously. Okay? Now, banks don't do this continuous compounding because people would freak out, I guess, and nobody would understand it. But compounding continuously gives rise to this formula for your money. Exponential growth model, this exponential growth. So if you're going to put your money into an account that's compounded continuously at 4%, you would get, your money would be, the amount of money that you would get would be in here. Let's do it. Let's suppose you did it for 1 year. Okay? You put in $1,000 and you want to know how much that's going to give you. What did I say, 4%? If you could get 4%. No bank's going to give you 4% nowadays, but this is what you would get over any period T. So if you put this in for 1 year, how much is your money worth? It's 1,000 e to the 0.04. Somebody do that? E to the 0.04. We got an e to the x. Somebody do that for me? 0.04 e to the x and multiply by 1,000. How much money would you have then?
Thanks.
Do anybody have it? You got an error?
I don't know how to use this.
Oh.
How do you get the T out of there?
The t, I said t is 1. Let t be 1. Okay, at t equals 1, here's what I want someone to do.
0.96.
Okay?
Are we multiplying by 1,000?
Yeah. Do e to the 0.04 and multiply by 1,000. That should be too bad. You got an e to the x.
60, right?
What is it?
560.
Oh, you lost money. This is not a good thing. Okay? Don't invest in that bank. All right? This is not good. Vitaly, what you got?
I got 1,000.
What did you get?
What's in 91.82?
Thank you. Okay, so 1491, 32. Okay, good.
Oh, never mind. I got 1,040.
82.
Yeah, I got
1,040, yeah,
1,040.
1,040.
I got 1,000.
Wait, they got 1,040?
Yeah, 1,040, 81.
All right, well, I'm going to go to Gessner's Bank and do that bank, okay? And that's what I'm going to do. All right, so anyhow, you got 1,040, but I bet you there's some decimal after that down a ways, because it should be a little bit greater than that.
Yeah, it's 1,040.81.
Oh, well, that's better. Okay, so 1,040.81. Okay, what does this mean? 4% is called the APR, okay, annual percentage rate. The 4, what is this? Effective annual rate. It's 4.081 is the effective rate of interest, because after 1 year, you ended up getting this amount of money, which is not just the $40, 4%, it's the $40.81. You get that extra 81 cents, which means that the effective rate is 4.81%. No, 4.081%. Which is not a heck of a lot better, but it is a little bit better. Okay? That's called the effective rate.
81 cents over the course of the year.
Yeah, 81 cents, that's right. What can I tell you? Peanuts.
So what's 20% per day compounded?
Okay, we can do that. We'll go do that problem. Before we do that problem, though, I want to point out one other thing. All right, hold on. All right. One thing. What's that more realistic population growth model? This is time, population. I just gave you exponential growth like this, which is unrealistic. No organism will increase exponentially over an extended period of time. Resources get exhausted. There's no food, oxygen, whatever. Something happens. Okay? What's a more realistic model? The model that's actually used nowadays, or one of the models that's used, is this. It will start off exponentially, but then we'll do this kind of a thing. What's that? Well, no, actually, as long as it doesn't die off, okay, because predators just eat it or whatever, it will stay pretty steady, okay? This is called the carrying capacity of the environment.
Oh, I thought you were talking about the petri dish.
The petri dish, they'll die out of this because the food will go away, yeah. The carrying capacity of a petri dish is 0 because the food is exhausted. But if you were to take a population of turkeys, say from Massachusetts, and put them somewhere in Minnesota because they don't have any turkeys anymore, and you want to have, they want some turkeys over there, so you take some turkeys from here, you put them over there. Now, if they're not immediately killed by the wolves in Minnesota or the coyotes or whatever, and they do survive, they will have exponential growth initially, but then they'll level off to what's called the carrying capacity of the environment. This function's a little bit more complicated than our function of population growth, but it's not much more complicated. As a matter of fact, when we get to partial fractions a little bit later on, we'll come back to this. This is called a logistics function. Okay?
What's the human one look like?
What's that?
What's the human population?
The human one is, here's the human. It depends on where you want to start. Okay, here. But it's like this, though. Because around the 1800s, 1700s, 1800s, that's when the population of Earth really started taking off. Wicked exponential growth. But it's been leveling off, I think, recently, right?
I hope.
I think. Although maybe this is too unrealistic. Maybe it's...
You forgot the flood where you got destroyed.
Oh, yeah. Well, here it is. It's a little blip right in here. Okay.
No, it was higher than that.
All right, whatever. All right. Anyhow, yeah, human population is interesting. Okay, so let's do the actual problem on the sample test. Let's take a look at that. The sample test, the last problem on the sample test is a population growth one. Okay, so what do you have? You have P is equal to P sub naught e to the KT.
Could you all like number or someone that way when I take a picture of it?
Oh, man, okay.
Not too much.
Okay, wait a second.
19.1.
1, 2, 3, 4, 5, 6. I think this is like page 7.
No, not the page.
Oh, what?
The number of the problem.
Oh, this is number 19 to 20 on the sample test.
There you go.
Okay. Okay, so what do we know in this one? 20% per day compounded continuously. So K is the 20%. Okay. Compounded continuously means that they're always increasing, okay, over this interval of time. It's not a discrete thing where at the end of 5 minutes, it all of a sudden jumps up, and then at the end of another 5 minutes, it jumps up. It's a continuous growth model, okay? Just means they're always,
I believe you.
they're always multiplying here, these bacteria, all right? Hey, whatever. Okay, initial population is 1,000. Well, let's see, what do we have? Streptococcus or something like that in your throat. You got 1,000 bacteria in your throat. They're increasing 20% per day, compounding continuously. We want to know at the end of 7 days, do you have the symptoms of strep throat? I don't know how many bacteria you need to get the symptoms, but who knows? So, population at any time t is 1,000 e to the 0.2 t. Well, the first question is, what's the population at 7 days? After 1 week, okay, so at t equals 7, the bacteria would be 1,000 e to the 0.2 times 7. That's equal to 1,000 e to the 1.4. Now, I need someone to do this.
Why 1.4?
So this is pretty.
0.2 times 7. It's very simple.
Oh, I got 1,055, but
1,055?
4,000.
Oh, 4,000. Okay.
But maybe I'm wrong.
You agree with him, Gester?
Yeah, that's right.
0.2 times 7 is 1.4.
No, it's
It's
4055.19 or 99.
Wait, so is this okay?
Yes.
Yeah.
Okay.
Point
It's
1996.
0.199. but-
You
Point.
can't have .19 thing.
Yeah, that's right. Forget it. Round it. Use a floor function to round down. 4,055 will round down to 4,055.
Well, you could have a half mosquito, I guess.
Count that
Yeah, well, whatever.
as
Okay, that's how many you have after 7 days.
So that's 19, right?
This is being recorded.
The other question is, what's the doubling time? Well, obviously, we've gone past the doubling time. We've got quadruple time here. But let's find doubling time. To find doubling time, this is what you do.
You just equal it to.
Okay, yeah, you need P to be 2,000. So 2,000 is equal to 1,000 e to the 0.2 t. Okay?
You have to find the, use the natural log here, right?
Yes, you do. Divide by 1,000. Now, let me just pause here a second. I'm going to find the time it takes to go from 1,000 initial population to 2,000. I'm going to find that time. That time will be the same time it takes to go from 1 million to 2 million, or from 100,000 to 200,000, or from 50 to 100. Doubling time in exponential growth models is a constant. It doesn't matter if you're going from 1 million to 2 million or from 1,000 to 2,000. The doubling time is the same. It's this ratio that's equal to 2. Okay? So doubling time doesn't even matter. That reminds me of a problem. You ever hear this problem here? You got a little pond, like we have a little pond in our backyard, and it gets covered by lily pads, let's say, okay? The amount of area that the lily pads cover in the pond doubles each day. Okay? The amount of area covered by the lily pads doubles each day. At the end of 30 days, the pond is completely covered by lily pads. At the end of which day is the pond half covered by lily pads? 15 is the one that people say that's not correct.
The acceleration is.
So the answer is 29. Who said? At the 29th day, it must have been half covered because the next day it doubled and covered the whole pond. This is 29. I just reminded me of that problem, that's all. Okay, so how do you find T here? What do you do to each side?
You do the natural log.
Do the natural log. Okay. Natural log of 2 is equal to the natural log of e to the 0.2t. What's natural log of e to the 0.2t is 0.2t. Okay.
The answer is 3.4657.
Okay, well, on the test, I'm not going to ask for this. Here's what I'm going to ask for. What you're going to do now is divide both sides by 0.2. So t is the natural log of 2 over 0.2, but I'm not going to ask for it in that form either. Okay? 0.2 is 1/5. When you divide by 1/5, it's the same thing as multiplying by 5. So it's going to be 5 natural log 2. Okay? You can think of this, multiply numerator and denominator by 5. 5 times 0.2 is 1, and you get 5 natural log 2. Would you say the answer was how many days?
It's like 3.
That's about right.
46.
Yeah.
I checked it.
Okay, that's good. Okay. Any questions on this? This is the answer I'm going to be looking for on the test. Okay? Right here. All right. We got one more topic to cover. Now we got radioactive decay. You're going to get one of these two problems on your test. And the sample test, and then I haven't gone over the sample yet either. We'll do the sample in a minute. We did some of the problems, but we're going to go through the whole thing.
What was the answer again? 5?
5 natural log 2. In radioactive decay model, what happens is this. In something that's radioactive, it decreases over time. It decays, okay? Uranium-238 decays into uranium-235, which eventually decays into lead, okay, over an extended period of time, all right? If you let Q equal the amount of radioactive material, and this is radioactive material, this is 2 words here, I don't know why they're so jammed in here, but
It's the same formula.
it's almost the same.
Almost.
Almost the same. But what happens is the amount of radioactive material decreases over time at a rate that's proportional to the amount of radioactive material. It's the opposite of K, where K is some positive number still, but now it's a negative number there. What happens is you get this. Okay, and at T equals 0, Q is Q sub naught. It decreases over time. That's a radioactive decay model. These things are extremely accurate predictors, unlike our population model, which is only accurate over a short period of time. This is very accurate over an extended period of time. Okay? So what happens? You go through the same thing I just did. Everything is the same except the very end now we're going to have a negative K instead of a K. So what happens is Q is equal to Q sub naught E to the negative KT. Okay. That's a radioactive decay model. Now what you may see is something where you have to compute half-life. Okay? Half-life. So let's suppose that we have, and this model in 1955 was used for carbon dating, okay? Carbon dating, and now we have dating on the internet, so you can just do it that way. No. All right, carbon dating, where you can take a fossilized bone of some kind and look at the carbon-14, this was the way it was done originally, and carbon-14, radioactive isotope carbon, decays over a certain amount of time. Its half-life is like 5,280 years or something like that. And by measuring how much radioactive carbon is left in that bone, okay, you can find out how old that fossil is, okay? And now they don't use radioactive carbon, they use something else with a really long half-life, so you can get this measurement really close. And they're really accurate with these kinds of things. But he won the Nobel Prize in '55 for discovering radioactive dating, this carbon-14 dating, okay? And this is the model that was used. This is how it was done. All right, so let's suppose that the original amount of carbon-14 or whatever it is, or something, is 1,000, well, let's say 100 cubic centimeters, okay? No, we got to do weight here, okay? Grams, okay, grams. It's a weight thing. Okay, so the original amount of radioactive carbon-14 is 100 grams in this dinosaur bone or whatever the heck it is. And let's suppose at T equals 50 years, because we can find another fossil, let's suppose the amount of radioactive carbon in that same specimen goes down to 80 grams. Okay, so we know the original amount, and we know after 50 years it decreases, the amount of radioactive carbon decreases to 80 grams. Given those two pieces of information, can we find the half-life of this radioactive material? The answer is yes, we can. Let's take a look. Q is equal to Q sub naught, e to the negative kT. Original is 100 grams. Okay, that's the original. At 50 years, the amount of material, it's not Q sub naught anymore, the Q is equal to 80 grams. Q sub naught is what it is at T equals 0. Okay, so after 50 years, the amount of radioactive material is 80 grams. The difference between this problem and the previous problem is I gave you K in the previous problem. We knew the rate of decay or the rate of population growth in the previous problem. In this one, you're going to have to solve for K in order to use K to find the half-life. Okay? You with me, Melissa? All right, hold on. Let's see what we got. So Q is 80 grams at the time of 50. Okay, divide by 100. Okay, take the natural log. The natural log of e to anything is that anything. Divide by 50, negative 50. So k is equal to natural log of 0.8 divided by negative 50. Okay. Yeah, let's do an approximation here. I need the natural log of 0.8 over negative 50. We should get some positive number because K, we said. Good enough. Good enough. Thank you. All right, that's K. Let's use K to find half-life. Let's find the half-life. Okay, so here's what we know. Q is equal to Q sub naught, original, 100, e to the negative k t. You with me?
So half-life we're looking for T, right?
We're looking for half-life is at T. The time it takes that radioactive material to go from 100 grams to 50 grams, which is the same time it will take to go from 50 grams to 25 grams. Which is the same time it will take to go from 25 grams to 12.5 grams. That half-life is a constant, okay?
It has to
So,
be negative exponent.
what's that?
It has to be negative.
Yes, the radioactive decay models will always have negative exponent there. So let's find T that gives us a Q of 50. That'll be the half-life. Divide by 100, we get 1/2. Okay. Take the natural log of each side. Okay. And divide by that coefficient of T. So T is equal to, the half-life is equal to, the natural log of 1/2 over a negative 0.0044. I don't know. We know that has to be greater than 50 years because at 50 years it lost 20%. So 100 years, 200, I don't know, a couple hundred years. Yeah, all right, that's about right. Not much of a half-life here. Not much of a life, you know. just decaying your whole life. You know? All right. Any questions on that? So on the test, wait, what did that mean, Vitaly? Does that mean you have questions?
No.
All right.
It's always fun.
Well, I made it seem like what are you, crazy? Of course I got questions. All right, that's what it sounded, that's what it looked like. All right, that is everything for the test, okay? You're going to get one of those two questions on the test, a population growth or a radioactive decay on the test, okay? Let's go through the sample test right now. Let's go through them all. Okay?
Wait, what are we doing now?
We're going through the sample test.
I thought we just did that.
Well, we did some of them. We didn't do them all of them. We did a lot of them, but not all of them. The test on Monday is going to look very similar to this, except it will be multiple choice. Okay? We understand that? So you really want to make sure you can do these problems. Okay? All right, let's go through it. Number 1, solve the differential equation. What do? We separate the variables. Integrate each side. That is the solution. Okay? How do we know that's the solution? Oh. Take the derivative, yeah. Take the derivative. Is the derivative of this function y x squared? Yeah, take the derivative, you get the x squared. Number 2.
Is that x cubed?
That's x cubed over 3. Second one, dy dx. Cosine x. Okay, but this one we're given an initial value of 0, 0. What do? Separate the variables. If you take differential equations, the course differential equations on day 1, you do separating variables. And that's it. Day 2, you do something else. All right? So like 1 day of diffy cubes, okay? Integrate both sides. Integral cosine. Okay. Now, we have to solve for the constant since we're given this initial value. Okay? So, let x equals 0, y equals 0. So y equals 0 when x is 0. Sine of 0 is 0. Constant is 0. Therefore, the solution to that differential equation with this initial value is y equals sine x. Everybody all set with that?
So what you did was find c,
Yes.
which equals 0.
Correct.
And then sine x is just answer.
Yeah. Yeah. 3. Find the average value. You find the average value by taking 1 over b minus a, the integral from a to b of the function dx. What is the average value? It's the height of that rectangle whose area is equal to the area under the curve. The length of that rectangle is the length of the interval. The height of the rectangle is the average value of that function. Okay? So, number 3. Here, why don't you guys do it? You guys do it. I'm talking way too much here. You guys do number 3. Oh, you already got it. Wow.
Is your number 3 different than mine?
I have the square root of x from 0 to 4.
Oh, okay, never mind.
Oh, I see what you mean. Oh, no. I just give you the formula here.
Oh, okay.
Yeah, yeah. And then 3 is, the actual number 3 is, y is the square root of x, and the interval is 0 to 4.
What is the formula? What is it? Can you just read it to me again, please?
Okay. The average value of a function, v average,
Yeah.
or maybe avg or something I should have put, is 1 over b minus a
Yeah.
times the integral from a to b of f of x dx. You got it, didn't you?
No, I have a question.
Oh. What's your question?
One here.
0 to 4. 0 to 4. Yes, you do go 4 to 3 halves. Because you 4 to the 1 half, because you square root of 4 is 2. It's cubed, it's cubed. But you put the 0 here and you put the 4. Okay.
0 to 4.
Yeah. 0 to 4. Okay.
We did ask about it.
Yeah. Then I realized.
All right, who's it? Wait, did I even take attendance here? I started to, I think, and then
You take it then?
I don't think I did.
So right here. Natasha?
Oh, I have it here. All right, Ludmila's here. Melissa's here. Ed's here. Nick, where's Nick? Yes, Nick's here.
Times 2.
Damien's here. Trent's here. Chris, Janice. Dolly's here.
No.
Other Nick. Tyler, I don't know. Lost Tyler. Gester's here.
Plus 1.
Eric is here.
I got that.
Okay,
And
that's
then
Eric.
you have to,
Where's Ed?
I think the denominator 3
Ed's
halves as
here.
well.
Okay, Ed's here. Eric's
So,
okay. Danielle's here.
so wouldn't it be 2
Jeff's
times
here.
the 3 halves?
Gabriel.
Right.
Yes. And
Yeah, you said 8.
Adrian.
Yeah, plug it in.
Yes.
And I got 8.
Okay.
Oh, very nice. Good deal. Nice.
Yes, it seemed about 3.
Oh, you said 8. You said
Wait,
the answer was
it's not
8.
8. It's not 8. It's not the answer. No, I got that, but I just thought.
Okay. Who's got an answer? Average value?
16 over 3.
16 thirds, he said? You got one? What did Vitaly got?
4 thirds.
4 thirds. Ooh, 4 thirds. He said it with a lot.
It's 2 against 1, so.
Yeah, but he said it with like,
Sorry.
anybody who disagrees with me is crazy. All right?
Oh, wait a minute. Maybe
See?
that-
You convinced him.
1/4 into it. So 1/4 times 16 thirds would probably
Be 4 thirds.
Oh,
There you go.
Yeah.
That's what I got. I forgot that part.
Okay, let's do it. So, what do you have? The average value, 1 over 4 minus 0, 1/4, the integral from 0 to 4, square root of x, dx. Okay? The integral from 0 to 4 is the area under the curve. Take 1/4 of it, okay? That'll give you the average value. That'll give you the height of that rectangle whose area is the area under the curve. Its average value. So it's 1/4. The integral of x to the 1/2 is x to the 3 halves times 2 thirds from 0 to 4. We can take this out. 2 goes in there twice. You get 1/6 here. We've got x to the 3 halves. 1/6. 4 to the 3 halves. So how do you do that? You take the half first, the denominator. That's the square root of 4. It's 2. Cubed is 8. 0 gives you 0. You get 8/6 or 4 thirds. Okay. 8/6 or 4 thirds. I don't know if I said it right.
How do you get
Yes.
1/4?
The 1/4 is 1 over b minus a. That's what this is. Okay? 1 over b minus a.
Oh, and
You
you got
get
that one.
2x.
What's that?
You get 2x.
How did I get what?
2x. 1/4 2x over 3.
It's 2 thirds.
2 thirds x. Okay, because this is x to the 1/2.
Yes.
And how do you integrate that? You add 1 to the exponent and divide by the new exponent. You're dividing by 3 halves,
yeah.
which is multiplied by the
Yep.
reciprocal.
Okay.
Yeah. Okay.
So then you just plug,
Plug the 4 in, plug the 0 in. Yep.
you do it twice though, right?
What do you mean?
You do it separately to each one, 1/6, 4.
Well, I choose to take a constant out front and then and keep them like this. You could do 1/6, put the 4 in, and 1/6 and put the 0 in, or take the 1/6 out
Yeah, but
front.
where did
Either
your
way.
3 halves go?
When you put the 4 in, you get 4 to the 3 halves. Here, you have this.
Yeah, that's.
And 4 to the 3 halves is 8. Okay?
So you move 4 times.
You take the, no. Here's what you do. When you do 4 to the 3 halves, you take the denominator first of that exponent. That gives you the root. That's the square root of 4. 2.
Just do 2 times.
And then the numerator gives you the exponent. So it's
okay.
2
I
cubed,
see
which
what
is
you-
8. Okay?
So-
You're fine. You're fine. Not a problem. You're fine. Number 4. That's an average value of 1 over x from 1 to 2. That average value is going to be, here we can just do it out. 1 over 2 minus 1, 1 to 2, 1 over x dx. That's the average value. This is just 1, who cares? The integral of 1 over x, natural log. We get natural log of 2 minus the natural log of 1, but the natural log of 1 is 0. We end up with the natural log of 2. The average value of that function from 1 to 2 is the natural log of 2.
Because natural log of 1 is 0.
Yes. Yep.
You just put natural log of 2.
Just leave it natural log 2. If you see that problem on the test, the answer will be natural log 2.
Nice.
Can you just go and do that again, please? I don't know.
Yes. I'm using this formula right here.
Yeah, I get that. I just don't know where did the natural log come from?
The integral of 1 over x dx is the natural log, absolute value of x plus a constant. That's that integration form. Now, I did not use absolute values because I knew I had positive numbers here, so I didn't need the absolute value here. That's all. But that's an integration form that we have. Okay? All set on?
If it's a negative 2, and let's say, and
Then you're going to need absolute values.
but it will still come out to the same answer, right?
Yeah, if you do, yes. Yes, it will.
Because you're using it.
Yeah, yes, it will. Number 5. A little bit more difficult, number 5. Average value is 1 over pi over 4 minus 0. The integral from 0 to pi over 4 of tan x. Now, 1 over pi over 4 is 4 over pi. What's the integral of tan?
It's 1 plus x squared, right?
No.
Is it square root of 3?
What is it?
Secant squared.
The integral of tan, the derivative of tan is secant squared. What is it? The integral of tangent is, what are you saying?
Secant square.
No. The derivative of tangent is secant squared. And let me tell you this. Throughout this whole course, this whole semester, it's going to be a constant problem getting mixed up with the derivatives and the integrals, okay? It happens all the time, okay? How do you keep them straight? You just have to crank out these problems. I don't know what else to tell you. The derivative of tangent is secant squared. The integral of tangent, however, is, it's one we did last time, I believe.
Natural log is secant.
It's you're in the right area. It's the negative natural log of cosine.
Oh, right.
Negative natural log of cosine.
Oh, right, because cotangent's positive natural log of
Sine. Yeah, that's right. That's interesting. Not many people get the integral of tangent by memorizing or knowing the integral of cotangent.
Yeah.
Almost always it's the other way around.
Derivative of tangent is secant squared.
The derivative of tangent is secant squared. That's a Calc 1 thing.
Then what was the 1 plus x?
The integral of 1 over 1 plus x squared dx is arctangent.
Arctangent, that's right.
I know, they all kind of sound the same, but the good news is all our integration forms are done, okay? They're all done. From here on out, it's applying them and then developing technique to arrive at one of those forms, okay? So that's the good news on that, all right? So, the integral of tangent is negative natural log cosine. Okay? So, what do we have? Negative 4 over pi. What's the oh gosh, here we go. What's the cosine of pi over 4?
Cosine.
Yeah, square root of 2 over 2, thank you. Well, you knew that one. And the cosine of 0? 1. Oh, jeez. And what's the natural log of 1?
0?
0. So forget about it. This is your answer right there.
Why do you ask that natural log of 1?
Because the cosine of 0 is 1, and the natural log of 1 is 0.
Because you do it separately out though.
Yes, yes, yeah. But I'm getting tired of doing these, so now I'm skipping steps, this is what I do. So if I skip a step and you want me to do it, ask, okay? Don't hesitate. Okay? You with me? Sounds like you are. I think, for all those times you missed, I think you're doing okay. What's that?
6 already.
I don't really get the last one.
Which one? The one I just did?
No, it's fine, I get it.
5.
What do you mean? Okay. What don't you
I
get?
just don't get the square root of 2 divided by 2.
The cosine of pi over 4 is something you should know. It's a cosine of 45 degrees. It's 1 over the square root of 2 or the square root of 2 over 2.
Isn't it minus 1? The minus 1 doesn't matter.
Oh, okay. The minus is the natural log cosine of 0. What's the cosine of 0?
Oh.
1. What's the natural log of 1?
Zero.
0. So that's why I didn't write it. Okay, that's 5.
Now we get the easy 3.
We got the easy 3. Number 6, what's the first step? What's the answer? Divide. 7. Oh, what's 7? Ooh, this is not easy. What's that? No, factoring is not going to help.
Complete the square.
Yes. Complete the square. Sorry. All right. This is complete the square. Because what you're going to end up with is what form here? I'm going to do it out. Let's do it.
Wait, did you do these? You did these out before I came in, Charlie, right?
What's that?
You did these out before I came in, right?
No. I did number 6 before you came in. We talked about that one because Melissa had a problem from the homework. It was very similar to number 6. But I did not do number 7. And number 7 you do this way. You say, okay, what do I have to do here? What must I add to this? Jeez. All right, I must add 1 to that to make it a perfect square. Okay, this is completing the square. But I'm going to subtract 1, since I added 1, and I have a 5. I'm going to add 1 and subtract 1. Why? Because now I can write it this way. Okay. So the answer to the question is, what's the first step is complete the square. I'm not going to ask you to do it out, but if you had to do the integral out, what integration form is this? What is it? Arctangent, inverse tangent. Very nice. That's exactly what it is. What's u in this case? X plus 1. The du is just dx, so I don't even have to multiply by anything. What's the integral? The integral gives me, okay, I've got u squared plus a squared here. Okay. A squared is 4, a is 2. Bless you. The integral is 1 over a, inverse tangent, arctan, u over a, here, I'm going to go right to there, plus c. That would be the integral. Okay? That's the integration form that we had.
Okay, so I'm going to say added 1 and you subtracted 1.
Yes,
Why did you add the 1?
to complete the square. So I had a perfect square here. I wanted a perfect square, x plus 1 squared.
Okay.
Okay.
And then the plus 4, just you subtract that 1.
I subtracted the 1 from the 5 to give me the 4.
Okay.
Fortunately, that came out to be a perfect square. I mean, it's conceivable that it doesn't come out a perfect square. It comes out to be 7. In which case, a is going to be what in that case? Square root of 7, yeah. Okay. All right, 8. Oh, and 8, what do you do first? What's the first step?
So let u equal
Whatever the square root is.
Yep, that's exactly right.
And you won't equal X plus 1, right?
I won't give you that as a possible answer. That would be a possible way to do the problem. I would not do that to you, David. Okay. U is the square root of x plus 1. What does that do for you? It enables you to get rid of the square root, change the integral from this, what it is, which we can't do, to an integral we can do. Okay? All right, 9. Oh, it says integrate each. And why don't you guys do 9? You're going to have some integrals here in this in the test. And I'll tell you what, number 9 is typical kind of thing you're going to see. So is 10. These are all typical. 9 through 12 are all typical. Once you do 9, then I'll do 10. Oh, you already got it? Take it easy, Danielle.
Yeah.
Wait for these other guys. They're not as
I
quick
wanna
as
ask
you.
you.
Oh.
I don't think it's right, it's fine.
Yeah, but the deal is you gotta multiply it by 2, so you end up with the cosine power of 2. And that's not that. The cosine power of 2 is.
Yeah, I do. Did it 0?
Yes, it's 0.
0. So then that would just be 0.
That would be 0, and then you gotta put the 0 on it. And the cosine of 0 is 1. Yeah.
And then is this okay? 2. Put 2 on
What?
here. Yeah. Put 0 here.
I don't really like, I don't know what this 2 is down here by itself. You got a negative 2. Because you let u equal 2x, so 2dx in cosine. This is very nice. So you get this negative 2. I'm going to chuck it up. So cosine over 2 minus cosine of 0. Okay? Now, negative 2. Cosine of pi over 2, you said was 0. Cosine of 0 was 1. That's the answer. If you put an equal sign here, I'm not sure.
I wasn't doing, I was doing like the second one, negative 2 cosine 2 pi over 4
Okay.
minus negative 2.
That's okay. That's okay.
Um,
That's okay, except the problem is when you put the pi over 4 in, you get a 0, and then it's minus, minus, plus. Actually,
Well, if you put the negative 2 in, sure, it would be plus 2.
yeah, it would. But I'm wondering what happened to, you get the cosine of 0 here, which is equal to 1, so this
Yeah, I
is
see.
slightly off, that's all. Whoa, so you did, this is pretty good.
Is that?
Negative root 2 plus 1.
Because is
Here's
there
the thing.
anything to the power of 0 1?
Yes, it is. But,
The integral sine is negative
Okay.
cosine. It's-
so, first of all, u is 2x, d was 2d,
That's
so
how
I
much
put
check.
2 in there on hand.
And I let u
And I have a
equals
one.
2i.
Why again?
Because u is 2x.
So du.
This is an e to the u form, where u is 2x, the u is 2d.
Huh?
Did you bring the 1/2 out?
You gotta multiply by 2 and by 1/2.
Oh, I didn't do the 1/2.
So you gotta have a 1/2.
No, you don't,
See,
because
that's
du
probably what
equals
there's-
2dx.
You multiply by
Yeah.
2 and by 1/2, so you get
Yeah,
this.
so then the integral is just negative cosine 1.
This is what you, this is your d
From
number.
0 to pi over 4.
So you end up with 1/2.
So then it's
to
negative
the u.
cosine pi over 4 minus the negative cosine of 0.
And now you're gonna get 1/2
Right,
e squared
yeah.
minus
And
e
the
to the
cosine pi
0,
over
which you
4
said was.
is root 2 over 2, but that's a minus, so it's minus root 2 over
That's
2.
your plus 1.
I thought, so,
Because you
I
said that's how
thought
you
it was
got
just
it.
e to x
Yeah.
equal e to the 2x.
I
I
agree.
know how the.
Yeah, but no, but see.
Then what'd you get?
I don't know.
It's not quite that simple, because you gotta get it at e to the u, u is 2x, you gotta multiply by 2 to get it. The integral of e to the u is e to the u, but you gotta get it to e to the u first.
It's right, because it was e to the 2.
Right now, it's e, yeah,
Okay.
it's off a little bit because of the 2. All right, how we doing? What are you guys doing, just this one, or you did all 4? You doing just this one? Serious?
I'm doing all of them.
Oh, wait, Trent. All right. I'm starting to lose it here.
The second one, you don't even have to do any substitution.
All right, why don't you do all 4, and then we'll do all 4, okay? Do all 4, what the heck?
The second one, they're still working on it.
So there was no substitution, why was
Well, because the integral of e to the x is e to the x.
The integral of e to the u is e to the u, but you gotta make sure you get to the e to the u du. U is 2x, the du is 2dx. You don't have a 2dx, you gotta multiply by 2 and 1/2 to get there. Once you get there, the integral of e to the u is e to the u. Okay, but you're not there at the moment. You gotta multiply by 2 to get there, and by 1/2 to compensate. So, looking at that Red Sox jacket, are you a major Red Sox guy?
No,
Oh, you're not?
He's just.
No.
No,
Pitchers and
maybe.
catchers, what, Friday, tomorrow, right?
Yeah.
Psych, psych. Although I saw a picture of Pablo Sandoval, Panda. No, I saw a picture of him.
Yeah,
I mean, he's chubby. I mean, he's
Yeah.
real chubby.
he's quick.
Well, I don't know how
He
good
plays
you can
good
be.
games.
You're weighted 280 or so, you know?
Yeah. He's one of them.
Yeah, that's true. There are people like
Did you
that.
get this? Because I got this.
Thank you. This is perfect.
1.5.
Add this. Two minutes.
Okay.
Minus.
Alright, no more
You put the
sports
zero
ads,
in there.
Whatever it is.
Zero doesn't give you zero. That's the problem.
Oh, yeah, it doesn't.
I thought you were mad. I was like, okay.
All right, how we doing? You doing okay?
No, distraught.
No support.
Let's go over it. Let's just do it.
Okay, you want me to do it right now?
Yeah. I think we're ready.
You think you're ready?
And even if we are.
Yes. Or is it the first two?
Yes, I'm ready. All right, never mind. Okay. All right, number 9. The integral, 0 to pi over 4. 2 sine 2x dx. What you're always looking to do is take the integral that's given and put it into an integration form that we have. The integration form for this is sine u form. U is 2x. The du is 2 dx. Well, the 2 is already there. This is good. We're going to use it. I'm going to rewrite it. Sine u du. Okay? And what I mentioned the other day is that what you can do at this point is change your limits of integration. These integrals are so simple, you might as well just leave them as x's and go back to x's. Later on, when they get more complicated, we're going to want to change the limits of integration as we change the variable, as we make these substitutions. But right here, it's just simple enough to just leave them in terms of x. What's the integral of sine u? It's a negative cosine u. Now I'm back to x's, so I don't have to specify x equals. Substitute in, I get negative cosine 2 times pi over 4, which is pi over 2, minus plus cosine of 0. What's the cosine of pi over 2? Cosine of pi over 2 is 0. Cosine of 0 is 1. Is that what we had, Danielle? Is that what we had?
Yeah.
Okay.
2. Now 1?
1.
Oh.
Yeah,
You wrote 2.
I know,
Wait, yeah.
2. No, because we needed the 2. We need the 2 to serve as the du. U is 2x. No, the du is 2. I need this 2 to be the du. You don't have to 2. You see what I did?
Wouldn't it be negative 1?
No, because you still get the negative here.
Oh,
Okay.
According to Haddad, I'm in Burnsy's class.
According to Haddad, what?
I'm in Burnsy's class.
Burnsy's class.
Professor, where did you get the negative, well, I know you got the negative cosine, but where'd you get the 2 pi from? Or pi over 2, rather?
It's 2 times pi over 4.
Yeah.
And 2 times pi over 4 is pi over 2.
Oh, okay.
2 goes here once, 2 goes in
Oh,
here.
okay, yeah, I see what you did. All right.
Okay. Danielle, are you okay with that now? I need that 2 to serve as the du. Okay, it's not here anymore because it's in here in the du part. So make sure you got that all right. Yes?
How come you don't have 1 over b minus a in front?
Because it's not an average value problem.
Oh,
That 1 over b minus a you use for an average value problem. Okay. This is just a straight integral. This is the area under the curve. We're not looking for the average value of the function, where you take the area of the curve and divide by b minus a, the width
what
of the
about
interval.
the plus cosine 0?
Yes, because it's minus gives you a plus. Okay? Okay?
Where did there's supposed to be like one day? 1.5 or something like that?
No.
You don't remove the constant like that for these?
What's that?
You don't remove the constant like that for these or nothing?
Here's the thing. If this 2 were not here to begin with, I would then have to multiply by 2 to get it there and compensate by a 1/2 on the outside.
That's right.
But because the 2 is already there for you, you can use it as part of that 2dx to give you the du. The problem would have been easier probably if I didn't give you the 2 and you had to multiply by 2 and by 1/2. Okay. Number 10. Now this is one I don't give you the 2, you're going to have to get the 2. What form is this? E to the u form. What's u? 2x. What's du? 2 dx. I have to multiply by 2 and divide by 2 or multiply by 1/2. So now I have this integral.
Why do you do that? Why don't you just put half du equals dx?
I don't like that. I don't like that way of doing it. People make mistakes with that way. Really? Wait, you watch. When we get to the more complicated integrals later on, people who do it that way will make 3 times the mistakes as those people who do it my way.
Because it's more visual.
Because you know what your goal is. Your goal is to get that integration form, and that's what you work for, that goal. And I think it's better. I think people are better off doing it that way. So here we go. Here's the integration form. Let's do it. It's the integral of e to the u. It's e to the u. What's u? 2x. Put it in 1, you get e squared. Put it in 0, you get e to the 0, which is 1. Okay? That's your answer right there.
E to the 1 is 0, right?
No, e to the 0 is 1.
No, I'm saying e to the 1 is 0, right?
No, e to the 1 is e to the 0 is 1.
Okay.
Okay.
So when you have an e in a problem, you want to leave e there. You don't want to.
Yeah, I'm not going to ask you for this to 3 decimal places or something. You're going to leave the answer in terms of e. Yeah.
When you put the 1/2 and you put the 2 back in, wouldn't they cancel out that way?
Okay, what are you saying now?
First part,
Right back here?
all the way back. Wouldn't it cancel out the 2?
Yeah, if you want to cancel them out, then you're back to where we started. That's not good. You haven't made any progress. I need this 2 inside to serve as the du.
So you can substitute.
Okay, that 2 dx, yeah, so I can substitute for the du. The 1/2 will stay. Yeah, if you just cancel these out, then you're back to the beginning, and what are you going to have to do? Multiply by 2 and by 1/2 again. Then if you want to cancel them again, you're still back at the beginning. You can go on forever doing this, you know what I mean? And that's not good. This is like, who's the guy pushing the rock up the hill? Sisyphus, right? Pushing the rock up the hill and it rolls down, and he pushes it up and it rolls down again. Never mind that. You guys don't know that stuff. All right. Greek mythology stuff, yeah. All right, number 11. 0 to 1. 1 over x plus 1 cubed. What form is this thing? U to the n form. That's good. U is x plus 1. Okay. Du is dx. I don't even have to multiply by anything. What do I have here? I have the integral from 0 to 1 of u to the -3rd du. It's a u to the n form. Nice. Integrate it. It's u, add 1, and divide. 0 to 1. Okay. I'm going to take this -1/2 out. I'm going to put a 1 in here. 1 plus 1 is 2 to the -2nd. 2 to the -2nd is 1/4. Minus. Put a 0 in here. 0 plus 1 is 1. 1 to the -2nd is 1. This is a -3/4 times a -1/2. That is a 3/8.
Where'd the 1/2 come?
The 1/2 comes when you add 1 to the exponent, you get -2, and you have to divide by that new exponent. The integral of u to the n is u to the n plus 1 divided by n plus 1. That's the dividing by n plus 1 part is right here. This is the n plus 1. Check it out. Wait, what's wrong?
What happened to your exponent?
I evaluate. 1 plus 1 is 2 to the negative second is 1/4.
We can rewrite that technically, right?
What?
We can technically rewrite that, right?
Yeah, as long as you get 3/8, I don't care. You can write it any way you want.
So it'd be 1 over,
1 over x plus 1 squared, if you want to write it that way.
2 times x plus 1.
You could, okay, you could write it this way. Okay, you could write it that way.
And then you plug it in.
Then plug it in. Yeah, you could do that.
Okay.
What number is this, 6?
11. All right, number 12. We're getting there. 0 to 1. 4 plus x squared. What form is this? Arctangent, inverse tangent. A squared plus u squared. U is equal to x. Good. What's a equal to?
2.
2. So it's 1 over a, inverse tangent, u, which is x, over 2, from 0 to 1. Okay? We see this all right?
I'm a little confused.
Okay. The integral.
What's the u?
U is x.
U is x.
The du is dx. Yeah. So there's no need to.
So this is only for tangent, correct?
What?
Arctangent. Arctangent.
Arctangent. Yeah.
So that's u. What about the a?
A squared, I'm using this form. This is the integral, which is 1 over a, inverse tangent, u over a, plus c. That's the form that I've got.
What happens if you switch like x squared plus 4 instead of 4 plus x squared?
Doesn't matter. It's the same thing. You still get arctan.
Yeah, but like then you get the a's are.
No, the a is the constant always.
Okay.
The a is not whatever is first. The a squared is the constant.
Okay.
Yep. All right, so you get 1/2, inverse tangent 1/2. What is the inverse tangent of 1/2?
Inverse tangent.
Yeah, what's the angle whose tangent is 1/2? You guys know that? No, nobody knows that. Okay, inverse tangent of 1/2. No, no, because the tangent of pi over 3, tangent of 60 degrees square root of 3 over 2. I don't know what it is. Nobody knows what it is. Do it on your You can do it on your calculator. Be in radians. Inverse, do 1/2. What is it?
In radians?
Yeah, you gotta be in radians.
Oh, you have to be in radians?
Yes, you have to
It's
be.
like 0.46?
Yeah, who cares? All right, we don't know. And then you substitute in 0. What's the inverse tangent of 0? This one you should know. Inverse tangent of 0? 0. The answer is 1/2 inverse tangent of 1/2. Okay. If I were to give you that on a test, that would be the answer. Okay. I don't think I'd give you that. Okay. All right, that's 12. Turn the page. Oh, there's another one back here. Oh, there's 2 more back there.
No, we already did 14.
Oh, good. One more. What form was this guy?
It's arc sine.
Very nice. Arc sine. We got arc sine or inverse sine of 1/2. That you should know.
Arc sine of half.
Arc sine of 1/2. That's the angle whose sine is 1/2. What angle has a sine that's equal to 1/2?
45. 30.
What is it?
30.
30, yeah. Pi over 6. Got to be in radians. And the inverse sine of 0? 0. That's your answer, pi over 6.
So we got
That one, you know what? I would put that on the test and expect you to know the inverse sine of 1/2 is pi over 6. I think that's a tech math thing, okay? You should know the arc sine or inverse sine of 1/2. That's the angle whose sine is 1/2. 30 degrees. That's a geometry. That's a high school thing. Go
Can
ahead.
we use calculators?
Yeah.
Oh.
The problem with your calculator is if you put in radians and do inverse sine of 1/2, most calculators will not give you pi over 6. They'll give you 0.5 something or other, whatever pi 3.14 over 6 is a little bit. What do they give you?
Just divide.
What's that?
Which is
Could be about that,
Last
maybe.
semester I just did 5/2, 5/, which one matched?
There you go.
The approximate, but.
Yeah, you can.
You can just convert those multiple.
Well, see,
What does it give you?
Yeah, it's 0.5, but it's a fancy thing and it gives you the fraction too.
Ooh, there you go.
For that guy?
All right.
Good trade.
14 we already did. That's a Kashu
There's a lot
form.
of stuff.
The answer is A, number
Mine was
14.
graphs.
It was A, right?
Yeah,
A?
that one's pretty good.
I like this one.
Here we go.
Because it can go back.
I got the ones that they use.
You ready?
So I wouldn't
Yeah.
keep on.
15, what?
Yeah.
Ooh, this is tricky. The integration form for number 15 is what form is it?
Arctangent.
No, it's not arctangent. You know, and it looks like it should be, but it's
Wait,
not.
15?
15, what form is it?
Natural law.
Yes! It's
Why?
1 over u du form. That's how I have it on the test, 1 over u du. Because u is 1 plus x squared, du is 2x dx. You have an x up there, multiply by 2 and by 1/2, you end up with 1/2 the integral of 1 over u du. That's what that integration form is.
Can you show that?
Sorry.
Do you have
It's
to
all
do
right.
it that way?
Yes, you have no choice,
Oh.
because it's what I said. No, you have no choice. I just hit the wire.
Is it
That's it.
One.
Here we go.
I don't know what it's gonna be.
Yes.
sounds
You have
good.
25% chance of getting it right.
U is 1 plus x squared. Du is 2x dx. Multiply by 2, multiply by 1/2. You will have 1/2 the integral of 1 over u du. There's no other way to do this integral.
And that's exponential. No, that's
Natural log.
natural log.
That's well, if I were to give you in this section that problem, your answer is 1 over u du.
Why is it the 1/2?
Because I had to multiply by 2 to get my du and compensate by multiplying by 1/2. In order to get, what's du? 2x dx. Okay. Now, what's this form? Oh, I probably have it. Oh, I do. Number 17. What's number, let's do 16 first. What form is number 16?
Can we say it was sine, arc sine?
Arc sine, yeah.
No.
We got it wrong.
What form is number 16?
Arc cosine.
No, I wouldn't give you that. What is it?
Log of cosine.
No.
Shouldn't be one of those because it's a key, it's key.
It's none of those inverse tangent ones. What is it? No, because if to be a natural log, you'd have to let u be that square root, and the du is not going to be in form of x squared. I'll tell you what though, David, if you didn't have the square root there, it would be a natural log, it would be 1 over u du. Because you have the square root, what form, what is it?
U sub.
It's a u substitution, and you end up with what form? The form is, it's a u to the n form. Yes, that's correct.
Good.
All right, let's do it. Okay.
So you couldn't have done 15 with u to the n form? That's what I
No,
wanted to do.
no, because when you get 1 over u, the n is -1, and you can't use the u to the n form when n is -1. Because you get a division by 0 problem. It's a 1 over u du form. That's the only answer for that one.
So we just leave it like that, 1 over u?
Yeah, well, if it's in that section, that is your answer. 1 over u form. I'm asking for the form. And in 16, the answer is u to the n, okay? But I'm going to do it out to show you that it's u to the n. What's u in this case right here?
I have 1 minus x.
Yes. What's du?
It'd be 2x, 3x. Oh, 3x.
Multiply by -3 and -1/3. Okay, so I get -1/3 the integral of u to the -1/2 du. Du is this -3x squared dx. There it is here. This is u to the -1/2. That's a u to the n form. Right there. Okay? N is -1/2. U to the n.
How would you write the u to the n?
And the test, I'm going to have u to the n du. I think that's how I have it. I think. I may have just u to the n form. I'm not sure how I write it now, to be honest with you.
You probably put D.
I may. U to the n du. I'm not sure. But there's only one of them that'll be u to the n. Okay, so that's number 16. 17, what's 17?
Inverse of
Inverse tangent. Okay, that's will be your answer, inverse tangent. It's inverse tangent. What's that?
And negative, well, it's.
Yeah, that's it, inverse tangent. Arctangent, inverse tangent. I will write it this way, inverse tangent u. I will write it this way.
So if I put like 1 over a tan, like arctangent.
No, it's multiple choice, Danielle, that won't be a choice. You just click, you just put the answer for inverse tangent.
Or.
No, you don't do that. Okay, the answer is A, B, C, D, or E. E, none of these, and I'm going to tell you, E, none of these is a very rare answer.
You tell us one time.
I will probably tell you that E, if something, there is an E answer if there is on that test. Okay? All right, 18. What the heck is 18?
I don't know.
Inverse sine, yes.
Yeah, we did that.
What?
No,
No, wait, what do you want me to do?
we did this earlier.
18?
Oh,
I don't know if we did number 18
We
earlier.
did it. We
it
did
was similar.
Oh, okay.
It was
Oh, it was the secant one they had for homework. That's different, though.
Yeah, that's why I'm confused.
Okay, hold on. We're gonna do this. Damien, we gotta do this one. How do I do it?
I see how it's.
It's different. You don't have
It's
that.
arc sine, but
Yeah.
that's why I pulled up the homework because I was like, it's
What's u in this case?
Not that bad. It's
1 minus
important.
9 squared.
No.
I didn't know what it is.
U is not 1 minus 9x squared. What's u? 3x.
Oh,
Nice.
Iron, it just makes it rust. I mean, it's a.
Very similar to your problem.
The salt
Yeah.
is.
The du is 3dx.
So, it's,
Okay?
It's just highly attractive to like water.
So you got 1/3, the integral of
It's like
1 over,
highly
square root out, 1 minus u squared du.
You have a very big laugh on.
Yeah.
Was it heavy?
That's inverse sine.
Well, because salt, what it actually does is
It's
it
old.
raises,
We all set with
it
this?
lowers the freezing
Yeah,
temperature.
and then we
of
did
water.
19 and
That's what
20.
salt does, so.
We did 19 and 20.
By the salt causes snow.
We
It's lowering.
are done.
are we wicked behind?
One class behind.
Not bad.
We just made up for it today.
Hey, good
Are we still going to the lab?